This is important that when you move, of all the stuff that we've done each week, each one of these laborious tests, these assignments that I've been giving you, and so on and so forth, that you've been working your way through, and the 2 exams and so on. That was really nice. But at some point now going forward, you need to remember the basics, and by the basics, how to interpret what kind of data you need to collect, what data you're collecting, how you are going to apply which statistical tests you should be applying, and how are you going to apply them, and what the results of those statistical tests mean. Think about that before you start collecting data rather than after you collect data. Okay, so that said, so let's see, we have a whole bunch of this stuff here, right? So I'm going to work our way backwards a little bit. I'm going to start by looking at linear regression, which we introduced last week. So linear regression, you guys remember what kind of variables we work with when we're talking about regression, linear regression? When we're working with numerical variables, a lot of times we're dealing with the t-test, because we're looking for the average, comparing average of one group to the average of another group. When we're using analysis of variance, where again we're comparing means or averages against each other, except that we're looking at data that for analysis of variance, we're looking at situations where we have more than 2 groups that we're comparing, more than 2 means. Null hypothesis for t-test. Mean for group 1, mu for group 1 is equal to mu for group 2. The null hypothesis for analysis of variance. Mu for group 1 is equal to mu for group 2 is equal to mu for group 3, and mu for 4, and so on and so forth. We went through the reasons why you just don't reapply the t-test over and over again, right? And why you need a separate, and why you use analysis of variance, and then the post hoc tests to evaluate your data for those kind of situations. So we have a categorical variable and a numerical variable. Categorical variable is where your groups are. In other words, gender would be male and female. So you might be dividing up male and female and examining the average BMI for males and females, for instance. A categorical variable and a numerical variable. In this data set, if we were looking at BMI and we looked at ethnicity, we have eight ethnic groups that we have data for. So we might be comparing the BMI for each of the 8 ethnic groups. So we would use analysis of variance. From there, we moved on to situations where we would be looking for an association between 2 categorical variables. So for instance, whether or not a person has insurance, medical insurance, and whether or not they got a flu shot in the last 12 months. Okay, I brought this one up on person because I brought that particular pair of possibilities up because we're going to talk about that when we talk about the project data. Okay, so for each one of them, what would the values be for those 2, and what kind of variables would that be? So in its simplest form, are you insured? If they're going to have somebody respond to the question, are you insured? Would be a yes or no. I have insurance or I don't have insurance. You could take it a step further. Somebody says, yes, what kind of insurance do you have? Oh, they could have Medicaid, Medicare, private insurance, Obamacare. It could be a whole bunch of different kinds of insurance that they might have, right? So if we look at it most simply, we would have a categorical variable of insured or not insured, okay? So if we're interested, say, in what was the average age, if the average age of people that are insured is different than the one for people that are uninsured, we would be looking for the mean age for people who are insured versus the mean age for people who are uninsured. Aha, t-test, because we have 2 groups. Comparing means we have 2 groups. If we were examining for instance, for ethnicity, the average age within our population, from our sampling, average age in population for different ethnic groups, we would have 8 ethnic groups and 8 mean ages for those 8 ethnic groups. We use analysis of variance. But now let's throw a little twist in here. What about if we're interested in whether a person is insured or not, and whether or not they got a flu shot in the past 12 months? Well, now getting a flu shot in the past 12 months, we ask them that. they're going to reply either yes or no, or don't know, right? A lot of people don't know if they had a flu shot or not, I guess, but that comes up in any survey, right? In other words, you could conceivably have some missing values there. So at any rate, so if we're looking at whether or not a person is insured, one of two values, yes or no, a categorical variable, and whether or not a person got a flu shot, another categorical variable, and we want to see if there's an association. If people who are insured are more likely to get a flu shot, for instance, if we want to see if there's an association there, we have to look for an association between two categorical variables, something that we didn't consider up to this point because we were dealing almost always with numerical variables up to that point. So in that case, what did we do there? Well, as a reminder, what did we do there? We set up a contingency table, right? We set up rows. We put in some a variable like an exposure sometimes, maybe exposed to asbestos, not exposed to asbestos, an IV drug user, not an IV drug user. Usually in the rows, we put the exposure or what we think is going to be the independent variable that's going to determine what the other variable is. Okay, so in this case, we might put insurance, whether a person is insured or not, into the rows. So how many rows would we have in that case? Well, in the case of the simplest version of this variable, we have only two rows, right? Insured and not insured. So in the columns, we would put whether a person got a flu shot or didn't get a flu shot. So we have a 2x2 contingency table. In your head, if you want to imagine it, it's like very much like the tables that we drew up for diagnostic tests, right? Except we're looking at whether or not each row has what the frequencies are for each of the cells by row and column. Okay, so in that case, we have a number of options, right? We can do a chi-square test. And since it's a 2x2 table, and we're going to practice all this in a moment, since it's a 2x2 table, we can also calculate relative risk and odds ratio. Okay, but if I had done it with ethnicity and whether or not they were likely to get a flu shot, we have in the rows the ethnic groups, in the columns whether or not they got a flu shot or not. That would be like a 8-row by 2-column table. We could still do chi-square for that to see if there's a association there, right? A difference between the different ethnic groups. But we wouldn't be able to do odds ratios because we only do odds ratios for 2x2 tables. Again, we'll get a look at that in a few moments. Okay, so what kind of test we use? We use a chi-square test, right? And odds ratio and relative risk if the data is dichotomous, if it has two values, two rows and two outcomes. Okay, so now that leaves us with one more kind of set of data that we consider this semester. What about when we get a situation where we have two numerical variables that we're looking for an association? Okay, so in this particular data set, what might that be? Okay, so we have the age of the mother, and what else? What other numerical variable do we have here that the age of the mother might have some impact on? Well, how about the weight of the birth weight of the infant in ounces or in grams? So a possible research question for me might be, is there any association between the mother's age at the birth of the child and how much weight, what the weight of the infant was? Okay, and of course that's important because if the baby's underweight, if the mother smokes, drinks, or something like that, we might be interested in knowing, anticipating, understanding what the association between these two variables might be. Okay, so let's take a look at that. Let's start with that and work our way backwards. So I have the data open in SPSS already, and I just want to go into Blackboard and make sure it's available to you as well. Okay, and I know it's in like either last week's or the weeks before the same data set, but I want to make sure it's in this week's so you can find it easily if you're listening to this recorded or if you are working with us now. I'm going to put it into week 13 here. Let's see, it is in here. It's not there. It's not there yet. So I'm going to. Okay. Okay, I'm gonna move right up to the top there, make it easy to find. So we all have that available to us now, right? You can right-click on that on Blackboard in today's folder. Save that to your desktop. I've only given it to you we have it in other weeks as Excel files, CVS files. I've only given it to you now as an SAV or SPSS file because I want to encourage you to stick with using SPSS to learn how to be functional with SPSS. So watching a program last night from the 50s or something like that, and one of the things that somebody was going to business school, a woman was going to business school, which in those days was secretarial school, right? That's what women did. They went to secretarial school. There was more. What was the name of the school? What was the name? Catherine Gibbs or something like that. There was a couple of secretarial schools like Catherine Gibbs. I don't even know if they're still around. But one of the scenes in the movie is in the film or movie, whatever it was they panned over to the classroom, and it was rows of these women typing on these big old, black typewriters. And I remember as a kid, when I was in junior high school, they made me take a typing class. Actually learned on the same typewriters they were using. They had no letters on them, so you learned how to type touch, right? So how to get on this tangent? So I started to talk about these data sets, the SAV. Well, that skill, I know why I brought this up now. That skill turned out, and I hated it. I wanted to be in wood shop or something else. I didn't want to have anything to do with typing. But you want to know something? That skill was much more useful to me than any table saw that I could have been working on when I was in junior high school. Turns out that was an important skill because all was on these computers. Well, SPSS for you guys, as you move forward in your life in public health, if you're going to get involved in any academics or any kind of research or something like that, that's the skill with SPSS, with SAS, with these vertical programs, or programs for analyzing data, handling and analyzing data, they are going to be very important to you in the future. Take my word for it. So it pays to learn how to use them. Not to mention it's a little another notch on your resume or your CV, as they call it in the educational world, that you have this skill as well. Some of you guys may work for the Department of Health. You work at the Department of Health. They use a different program, SAS, but it's similar enough that your learning curve for SAS is going to be way shorter if you know how to use SPSS as well. Okay, so anybody on here now that's from the Department of Health, maybe? Did I get lucky? No, I guess not. Okay, nope. Okay, so at any rate, so you have the data set. You can save it to your desktop and give it a try along with me. So let's take a look at how we're going to analyze this data now. So I'm going to go back to the data view just for the hell of it. Okay, so we were going to be looking at the mother's age. Here's the column which represents the mother's age. Okay, and we're going to look at the amount of weight, not the amount of weight gained by the mother. That's also something we might want to look at, but the birth weight of the infant. I'm going to stick to ounces because the numbers are a little easier to observe and deal with. Okay, so let's take a look at it. First of all, let's see if we can determine if there's an association between, at all, if we can visually see an association between the mother's age and the infant's birth weight. Okay, so how would we do that? How would we first visually get some kind of rough idea if there was an association between the two of them? Right? Remember what we did last week? We looked at it graphically, right? We made a scatter plot, right? Let's do that. Let's go to the graphs. And again, as I told you before, I used legacy dialogues because I am a legacy. And I go down here to scatter dot. And I'm going to open that. And now, at this point now, it's going to ask me to decide which variable I want to put into the x-axis and which variable I'm putting into the y-axis. For what we're doing here, just looking for some association, it doesn't really matter which one I put into the X and the Y axis. Even when we do correlation, it doesn't really matter because correlation just is examining whether there's an association, whether there's correlation or association between two numerical variables. However, since later on, it's inevitably, I'm going to say to myself, well, gee, does the mother's age suggest that that as she's older, she might have lighter babies, more premature babies or lighter babies, or does the mother's age suggest that she'd have heavier babies? I might be interested in that. So I'm already thinking which of those is the dependent variable and which one is the independent variable. So the dependent variable depends on the independent variable in theory. So in that case, I'm thinking to myself, well, logically, it makes sense that the mother's age might help determine the infant's birth weight, one way or another. I don't know which way it's going to go. I don't know if older mothers are likely to have lighter babies or heavier babies, but I think there might be an association there. So I'm going to look at even though I don't need to now, I'm going to look at the mother's age as the independent variable and the baby's birth weight as the independent variable. So in general, we like to put the independent variable in the x-axis. So the age of the mother is going to get moved into the x-axis. And the weight of the child, the birth weight of the child is going to go into the y-axis. I'm not going to bother with titles and so on and so forth. I'm just going to go ahead and analyze this. I'll say, okay. And let's see what I wind up with. See what our graph looks like. Well, it's quite scattered, right? Pretty scattered. Well, one of the reasons it's lining up in columns like this is because the age is in integers. So there's a lot of women in this data set that are 25 years old, a lot that are 30 or 32. So you can see how variable the ages are. But you know, you can kind of almost see that there is, within each age, there's kind of a normal distribution. In other words, for women that are in this age range, you can see that there's kind of a center there, and that there's fewer and fewer babies within each age group that are, as you get further and further away from where that rough center is. So I'm going to double click on this and just get SPSS to draw a nice fit line to this for me. And I'm going to take a look at that. And you know, it kind of slopes upwards a little bit, right? Yeah, it doesn't look like a very strong association, but it looks like there is some sort of association there. It looks to me like as a woman's age goes up, the birth weight of her child is going to go up. Now, question is this really, number one, number one, from our perspective, is this statistically significant? Is it real, this increase, or is it just due to chance? And number two, is it clinically significant? Does it really make any, in other words, if it's statistically significant, it's easy to get something that's statistically significant when you have a big data set. Right? This is 800 subjects, right? Really a gigantic data set for us. It's easy to get a statistical significance when the actual, in other words, be able to prove that there is a difference, right? But clinically, the difference may not make much difference. It may not be really impactful. So we're going to examine that. We're going to be able to see that now as we work with this. So let's see. So I'm gonna minimize this for the moment, and I'm going to actually go ahead now and do that correlation coefficient, calculate that correlation coefficient. If you remember, if you played the lecture video from last week, it goes through how the values above, how a fit line is created based on the variability of the values below and above the fit line that you've drawn, so they're balanced. Okay, and we'll see what it looks like when we actually draw this. Okay, but I'm going to go ahead and how that the R value is calculated so that a very strong correlation could be a +1 or a -1, and no correlation at all is a 0 correlation, right? So that as we go from 0 to a higher number, from 0 to 1, as that number increases, it increases the correlation between the two variables, the association between the two variables. And we knew that as we went from 0 to -1, it gives us a picture of the strength of the negative correlation. In other words, a negative number for R means that there's a negative correlation. As the X value goes up, as the mother's age went up, that would suggest that the birth weight of the baby goes down. On the other hand, a positive correlation, a positive number would be as the age of the mother goes up, the birth weight of the baby goes up. And we're going to take a look now and see what that number comes out to be. So let's analyze this. Analyze, and we have a function called correlate. I'm going to go over to bivariate because we have two variables that we're working with. We're assuming that this relationship is linear, right? So that's why we're calling it linear correlation, okay? And we're going to move the two variables in. Now, remember I told you that for correlation, we're not assuming that there's any causality in here. We don't care which one is the dependent or independent variable, or if there even is one. We don't care if one variable is actually causing something, or it just happens to be associated in some way, through some other reason. Okay, so I'm going to move the age of the mother in there. Whoops. And I'm going to move the weight of the child in there in ounces. And I'm going to go ahead and do our analysis. I'm going to click OK. Okay. And our R value, our Pearson's R value, right, is, let's see, it's 0.168. It's a positive number. What does a positive number tell you? Positive number tells you that the correlation is positive correlation. As the mother's age goes up, actually it's better than I thought, based on what I saw on the graph, right? It's as the mother's age goes up, the weight of the baby tends to go up as well. Okay, so 0.168, 0.17, let's say. Is that a very strong correlation? No, not very, right? Okay, there's an association there, but it's not very strong. Is it real though? Is it due to chance, or is it a real association? Did we just get lucky on when you have 800 subjects, you don't really ever get lucky. But let's assume that's a small data set, a smaller data set than that. But it's just that this association that we're seeing just by chance, we just picked the wrong. Let's imagine that we only picked 30 people, 30 births instead of 800. Okay, is this association because we just happen to pick the wrong 30 people and it looks like that? Well, how are we going to take a look at that? We're going to take a look at the two-tailed significance, which is right below that. And you notice it's two asterisks next to that value. If we look down here, it says correlation is significant at the 0.01 level. Okay, in fact, it's actually the significance even lower than that. We can see that the significance is 0.000. Okay, actually, it's not really ever zero. It's always asymptotic. It's really less than 0.001. Okay, so that's how we would probably note it. But it's, in other words, we have more than 99% certainty that we wouldn't be wrong. And again, this is not the way real statistician would phrase this, but we have more than 99% certainty. We would be wrong if we reject the null hypothesis. Now, I brought up something now that maybe when you do real analysis, you want to consider at the start rather than at the end. I just brought up the idea of a null hypothesis. So if I were to put in the null hypothesis, I'm going to phrase the null hypothesis two ways. The first way is in English that anybody can understand. And the second way is in statistics that only statisticians and us can understand. Okay, so what's my null hypothesis here? My null hypothesis always starts out with that there's no difference, that there's no significant thing going on, nothing interesting going on. So in this case, my null hypothesis in English is that there's no correlation, there's no association, or in our words, correlation between a mother's age and the birth weight of her child. The alternative hypothesis in real English is that there is an association between the mother's age and the birth weight of the child. Okay, so even though the association is small, there's only a small influence that the mother's age has on this, right? We know that because it's not close to 1. It's really closer to 0 than 1. Even though it's a small impact, statistically, we can reject the null hypothesis. Why can we reject it? Because it's less than 5%. There's less than 5% chance that we would get this extreme a difference in the values, a change in these values from weight and the age of the mother, if the null hypothesis were true. Okay, if to wrap your head around it, you need to say that, oh, that means there's less than 5% chance that I'd be wrong if I reject the null hypothesis. Think that to yourself. Don't say that to a statistician, right? Or you get a fight on your hands, right? But I'm okay with that. As far as I'm okay with that. But a real statistician would, I think, have a problem with it, okay? But the real issue here is like anytime when you do the t-test, what you're really saying is that the probability that you would get that extreme an outcome if the null hypothesis is true is less than 5%. If you need to use the idea that that also means that there's less than 5% chance you'd be wrong by rejecting the null hypothesis, you can use that kind of as a crutch if you need to do that, okay? I'm okay with that. Okay, so I'm not militant. Okay, so now, in this case, what does this tell us? This tells us that this association is real, at least real enough for us to say, consider it, a valid assumption that we can use to go ahead in our research and to make decisions on, right? So since this is less than 0.05, if it wasn't less than 0.05, then we couldn't say that we're statistically certain. In other words, we couldn't reject the null hypothesis. Okay, so in this case, we can. But it's not really a strong association. So let's take this another step further. Let's say to ourselves, and again, we're getting to the point where we were leaving off last week. Let's say to ourselves, well, I want to have a better understanding of what kind of influence the mother's weight has on the birth weight of the infant. Okay, so I'm going to go, and I'm going to take this a step further, and I'm going to use a process called regression. So I'm going to go up to Analyze, Regression. And again, what kind of analysis are we doing here? Well, again, it's a linear regression. We're assuming that this data fits a straight line. Not all data fits a straight line, but we're assuming in our case it fits a straight line. And in linear regression, now notice in linear regression, instead of having a situation where it didn't care which two variables I put them in and which two I put in, now it's asking me to specifically identify which is the independent variable and which is the dependent variable. So what did we say? The independent variable was the mother's age in years. Yeah, and the dependent variable was the birth weight of the infant. Okay, that makes sense, right? Because would we do it the other way around? Would the birth weight of the baby determine the age of the mother? I don't think so. I mean, you might find an association, but it doesn't make sense, right? Okay, you might find there's a correlation there, but just as that, like I said, it doesn't matter which way you do it for correlation. But it makes sense to look at the age of the mother as the independent variable here, and the weight of the child is a dependent variable. Okay, so let's take a look at this. I'm going to say okay. So I'm not going to go into too much of the statistics here now. I'm just going to go ahead and perform this analysis, and then I'm going to cherry pick the information that I might use. For instance, if you're doing a project and you want to demonstrate an association and you want to describe how strong that association is and what it means, I'm going to take this from that perspective now. So I'm going to click OK. Okay, and if you'll notice, here we got a table down here. First thing it did was it calculated the Pearson's R value, the correlation coefficient, 0.168, just as we had before. And then it gives me something called R squared. And it doesn't take too much to figure out that R squared is literally the Pearson's correlation coefficient squared. It's 0.028, it's about 0.03, right? Okay, and then I'm going to go down here, analysis of variance, and you can see that's where our significance came from. There's our significance. Okay, wasn't that table wasn't provided before, but it was calculated before. Okay, and I'm going to pull this up so we can, if you're looking up there, you can see it a little bit better behind me. I'm going to look down here at the last box, which is called coefficients. And under coefficients, what we have now is we have the values that we need to describe that best fit line that we described, that we were dealing with when we looked at the lecture on correlation and regression. These values describe how to draw that best fit line. And how do they describe it? Well, for starters, let me just get a pen over here. For starters, this number that represents the constant, if you recall, this number represents the y-intercept for the straight line. And when we looked at the variable that's listed here, age of the mother in years, our independent variable, this represents the slope of the line. Okay, so if you're an old math major, you use the formula y is equal to mx plus b. Okay, I'm using a scratch pad over here because my trackpad's not cooperating. And if you're a statistician, you might use a little bit same thing, but kind of the same formula, but you might use something like y is equal to beta 0 plus beta 1 x, right? I think in your textbook, that's how they describe it. Every textbook I look at it's a little bit different, right? Well, both of these things really, both of these formulas are the same thing, right? So mx plus b, that's the value, that's the variable x, which is the independent variable. It determines the value of y, the dependent variable in this formula. The value m represents the slope of the line, and the value b represents the y-axis. Keep in mind, when you talk about the y-axis, why is that the y-axis? If x is equal, if you have an x and a y-axis, right, the point where x is equal to 0 is the point where the line crosses the y-axis. So if that's 0, then y is just equal to what b is, the place where it crosses, right? So in this case, it's m. In this case, it's beta 1, right? Okay, both of those represent the slope because they're multiplying the x value, the independent variable. And then b, or beta 0, those are where the line crosses the y-axis. That makes sense because that's all you need. If you know where a line crosses the y-axis and you know what its slope is, right, you can draw that line. So here's two different lines. They cross, the y-intercept is the same, but they have different slopes. But you can define the line just by the y-intercept and the slope. That can only be one line that fits that description. That's what we have here. So in this case, the y-intercept is 99.7 and the slope is 0.691. Okay, so what does that tell us? That tells us that I can create a formula Oops, I stretched that out and the line stayed still, but the table moved. That's unfortunate. Let me undo that if I can. I undo that? No, it doesn't work. Okay, but you get the idea. Okay, so I'm going to go over here and get a pen again. Okay, so now I can describe this formula as y is equal to, okay, and I'm going to use the math formula because I'm just a little bit more comfortable with that. The slope, which is 0.61, I'm going to call it 0.62, just make it easier, right? Plus times x plus 99.7. And I'm just going to put 99 there just to make our calculation a little easier. You shouldn't round anything until you're at the very end of your calculation. Remember, we always emphasize that because you're going to wind up squaring things, multiplying by things, adding things, right? You shouldn't do what I say, not what I do. Okay, I just want to be able to do this in a timely fashion here. So you shouldn't round anything in statistics until the very end, if you round it all. Okay, so 0.62 times the value of x plus 99 represents the value of our dependent variable y. Well, in our case, what is y? What is that dependent variable? That's the weight of the child. Weight of the child is equal to 0.62 times what's x? X is the mother's age. I'm going to put MA in there, mother's age, plus 99. Okay, something's wrong here. How did that happen? Should be minus sign in here somewhere. Is that a minus in front of there? Can't tell. Let's see. Did I get the right variables in here? Let me go back and take a look. I don't think all the mothers are over 99 years old. Oh, maybe I reversed what did I do here? Let's go back here. Analyze. See, it's good you see me make these mistakes, I think. Regression, let's see. Linear, independent variable is the age of the mother, weight of the child in ounce. Oh, okay, I'm sorry. We're good. Yeah, that makes sense. I'm sorry. I lost track of what I was, what the variables were, but we got it right. Okay, so what does this tell us? I feel more comfortable now that we got that right. Okay, so what does this tell us? That tells us if we know the age of the mother, if we know the mother's age, we have a formula that we can use to predict the weight of the child. Well, it's kind of a trite example. I mean, why might we use something like this? Okay, well, let's see. If one of the ways I might use this is if for some reason I want to be able to predict when babies are within a certain weight range, like maybe from, let's say, underweight or overweight or something like that. And this formula will help me determine help me understand the likelihood of the birth weight of the child being overweight or underweight based on the mother's age. Is it a good predictor of this? Not very good, right? Because we saw it wasn't that strong an association. The R value is only 0.17, I think it was, or something like that, right? So it's not a great predictor, but it's a way for us to predict that. In other situations, we might have other ways to use this. For instance, perhaps another way for me to use this is the slope here. The slope here is particularly important because the slope tells you, remember when we have look at the slope in math of a line, what we're looking at is the change in the y value over the change in the x value, right? In other words, how far across, if you go a certain amount across in the y-axis, in the x-axis, how much further up or down do you go on the y-axis? How much does the x value changing or the independent variable change affect the dependent variable? That's the slope. So in this case, the weight of the child, for every year that the mother is older, the weight of the child goes up 0.6 ounces. So if the mother's 10 years older, that would be 6 ounces more that we would expect the child to be, statistically expect the child to be, right? So why are we interested in something like that? Well, that helps us to determine how important that variable is. How important, for instance, if it were negative, if it turned out to be a negative slope, we might say, well, we should really encourage women to have babies at a younger age. If it's a positive slope and we want babies that are heavier, we might encourage women to have babies when they are a little bit older, not teenagers, early 20s, but a little bit older, to encourage larger babies or healthier babies. So we might use that slope that way. In other words, we might use that slope to help us make a public health decision. Okay. If we could predict, for instance, how a cholesterol level, a person's cholesterol level, affects how a person's BMI affects their cholesterol level. We might be able to then decide, should we invest a lot of public health money in educational programs to encourage people to lose weight or to grow taller, one or the other, right? They'll do anything you need to get your BMI lower, right? So if that's a small effect, we might say, well, the public health dollars are spent somewhere else, better spent somewhere else. If there's a dramatic effect, a large increase, in other words, a small amount of increase, decrease in the person's BMI reduces the cholesterol a great deal, that might be a very good investment of public health dollars. So the slope is important. So when you do a project, you might say to yourself, well, let me highlight what the slope means in this regression formula, what it's telling me. In this case, it's telling you for every year that the mother is older, the difference in the baby's birth weight is approximately 0.6 ounces. Well, is this really, so how much can I assume that this is really true, that this is really going to work this way? Well, there was a thing that we looked at there very quickly, which was called the R-square value. And this was all very nice, and now I'm going to deflate the balloon here, right? Okay, let's take a look at that R-square value. So R was 0.17, roughly 0.17. The R-square value is 0.17 times 0.17 is 0.03, roughly. So what does that tell us, that R-square value? That tells us that approximately 3% of the variability in the birth weight of the baby is determined by the mother's age. Well, another way to look at that is 97% of the variability in the baby's birth weight is determined by other factors that we didn't consider here, right? So, well, that's a bummer, because I mean, we didn't even look at those other factors, and we just spent all this time on something that is only a small impact on the actual birth weight of the baby. Right? However, now we understand what. Remember again, was this statistically significant? Right, it was. It's a real effect. It's statistically significant. Was it clinically significant? Maybe, maybe not. It's probably women that are older for a lot of reasons, better economic situations, more likely to be married, a lot of reasons why there might be this association. So yeah, it makes sense, and it's probably important, but there's a lot of other factors that look like it could be more important. Okay, so if you're going to do a project like this, you'd want to highlight, you want to discuss something like that. That might be something you might want to examine. And who knows, that might lead you down other avenues that of research that might help you decide whether or not perhaps I should look at these other variables instead. Well, let's look at the other variables that we have to work with here. Okay, so what are the numerical variables that we have here? We have weeks of gestation. Oh, wow, let's take a look at that. Okay, let's look at the association there. Let's see, analyze. Okay, and I'm going to go to graphs, legacy dialogues. I'm going to go to scatter dot. And I'm going to go to define. And I'm going to move these back. And I'm going to look at the weeks of gestation. I'm going to use that as the, where is it here? Wait, completed weeks of gestation. Use that as my independent variable and use the birth weight of the child as my dependent variable. Okay, so I am going to do that analysis. I'll say okay, and I'll see what happens. Oh, wow, there's a strong association there, right? Really strong, obvious association there, which makes sense, right? Now, this might be a little bit trite. We all know that, yeah, weeks of gestation is important because you have a premature baby, it's going to be underweight, it's going to be possibly life-threatening complications and so on and so forth. But even in the area up here where we're talking about the bulk of the normal births, you can see that there's an association between the weeks of gestation and the weight of the baby, right? So even if they're not like seriously premature, we can see that there's an association here, right? So now I'm going to leave it up to you to do a correlation and a regression, create a regression formula for the association between these two variables, the weeks of gestation and the birth weight of the child. So let's go back to our null hypothesis again. The simple English version of null hypothesis is that there is an association, there's no association between or correlation between the birth weight, between the weeks of gestation and the birth weight of the child, or there is an association between the weeks of gestation and the birth weight of the child. The statistician's version of that null hypothesis, the one you really should be using, is that there's no correlation. How do we say no correlation in statistics? R is equal to 0. And what's the alternative hypothesis if R is equal to 0? R is not equal to 0, right? Not 1, right? 1's only perfect, right? But you got the right idea. 1's a perfect, 1 or minus 1 is perfect correlation. We don't deal with perfect correlations, right? Ever, right? We'll never find a perfect correlation in public health. But R is not equal to 1. That's the way a statistician would say the same thing I just said before. Okay, so we're going to test that null hypothesis, and we're going to create a regression line so we can look at the slope and see what the association is between the weeks of gestation and the birth weight of the baby. Well, it seems kind of trite, right? Because we already know this is probably true. But think about this. That regression line, that slope of that regression line is going to tell us for every week that we maintain this pregnancy, how much weight that baby's going to gain. That's important to know. That's important to know because then you know that, gee, it's really critical that when we're in the 19th week that we get to the 23rd week. Or we're in the 23rd week, it's really, it's actionable information, right? So I'm going to leave that up. I'm going to take a break. I'm going to leave that up to you to work on. I'm going to give you 10 or 15 minutes for you guys online here, whatever, in here, online, wherever you happen to be, wherever the ship's at sea, as the guy, well, you guys wouldn't know that. I'm dating myself. I think that was Walter Winchell, I think, right? That, for you guys that have white hair, that was Walter Winchell. He used to sign off with that. Good night, ladies and gentlemen, all the ships at sea or something like that. But at any rate, I'm going to give you 10 or 15 minutes to work that out and come up with your own correlation analysis and your regression line. And we'll see how well you did on that, okay? So I'm going to pause.
This conference
Okay,
will
guys,
now be
we're back.
recorded.
Let me mute everybody again. And let me just check the chat box and make sure I'm not getting any questions here that need to be answered right now. Good. Okay, so we're back, I think. Yes, we are. And so let's analyze this data. Let's see what we wind up with here. So first thing I'm going to do is I'm going to go up to Analyze. I'm going to skip Correlate. The reason why I'm going to skip Correlate is because we know that when I do regression, SPSS is going to perform a correlation anyway. Well, what the hell? You might as well do Correlate, right? It's only one extra step. Bivariate. Okay, so this time instead of age of the mother, and weight, I'm going to leave weight of the child in there, but instead of age of the mother, we're looking at the completed weeks of gestation. And I'm going to click OK. And let's see what our Pearson's correlation look like. Well, look at this. This is a much healthier correlation, right? Almost 0.6. It's a positive 0.6. It's a positive correlation as the as we get more weeks of completed weeks of gestation, we get a higher birth weight. Okay, and in addition to that, we see also that is statistically significant. So this tells us that we can reject the null hypothesis that R is equal to 0 and accept the alternative hypothesis that R is not equal to 0. Now, both cases, we were able to say R is not equal to 0. In other words, there was a statistically significant correlation. In one case, it was only 0.17, the correlation. In this case, it's almost 0.6, the correlation. So we have much stronger correlation here. Both cases statistically significant. This one clinically much more significant than the other one was. Okay, so now that we've done that, now let's do we know that there's an association. It's a real association. Let's do our regression. Analysis, regression, linear. Okay, and this time, instead of the age of the mother, the numerical variable that we're going to look for an association with is the weeks of gestation. Child, let's see where it is, completed weeks of gestation. There we go. I'll click enter. Okay, and let's take a look first at the R value, right, which is just as we calculated it just now in our correlation. Okay, 0.583, so it's a strong association, positive correlation. And the R square value, the all-important R square value, instead of only being 3% now, is 34%. In other words, 30% of the variability in the birth weight of the infant is the number of weeks of gestation. Okay, that again still leaves quite a bit of room for other variables in here. And most things in life, in health and life, have a lot of variables. You can imagine all the variables that are involved in whether a person has a stroke, or whether a person has heart disease, or whether a person has diabetes, and so on and so forth. All of these things have like multiple variables that affect them. But we're in public health, we want to identify the ones that are real players, that are real important, and which ones can we affect, which ones can an intervention that we can put together, which one is going to have the greatest clinical effect. So in this case, much stronger association, weeks of gestation. Okay, and so if we create our regression line, if we calculate our regression line is going to be equal to, Sal, you may notice I'm scribbling here, but it's not very clear. It's because for some reason my pen's not working. I think the point might be bad or something like that, so I'm scribbling on my trackpad. So otherwise it's a lot better. So at any rate, so our regression line, so I'm going to use my math version. It's y is equal to mx plus b. You can use the statistician's version of this, but I'm an old engineer, so that's the way I roll. Okay, so what is y again? Y in this case is the weight of the infant, weight, right? And the weight of the infant is, the relationship is, it's equal to the slope, which in our coefficients, again, we know it's statistically significant, right? We've determined that, and we know what R and R square are equal to. Okay, the slope is let's see, completed weeks of gestation is 4.837. Again, do as I say, not as I do. 4.8 I'm going to put down here. Plus the y-intercept. Where is the y-intercept? Y-intercept is minus 70.411. That plus instead becomes a minus 70.4. I'm going to leave it at 70. So it's 4.8x plus minus 70. Okay, so what if the weight of the infant is 0? That's meaningless, right? There's no infant if the weight is 0. There's no infant with a weight 0. If it were 0, the weight would be, the y-intercept, the weight would be equal to minus 70. Keep in mind that the actual weight of the infant, right, excuse me, the actual value of the y-intercept is really more of an anchor for this graph, for this line, this regression line. It really doesn't necessarily represent a real situation or anything in reality. So that y-intercept, just look at it as part of that equation, not necessarily something that's really relevant to the association between birth weight and weeks of gestation. The other thing you should keep in mind is that whenever you do correlations or regressions, okay, a lot of times you'll get a graph and you'll be in the middle here and you'll be looking at people from age 20 to age 40, for instance, if you're looking at age as the independent variable, right? But then you might say to yourself, well, what about somebody that's 46 or somebody that's 17 or something like that? You should only consider that the data that you're working with, you should only consider that what you find, your statistical analysis, is relevant only to the range of the data that you're working with. You shouldn't extend your assumptions or your reasoning into areas where you don't have data. In other words, if you only have data for people that are 30 to 60, don't assume that your correlation holds up for people under 30 or over 60. Should stick to where the data is. Okay, and similarly, the y-intercept usually is just a placeholder for the line, a way to draw the line. Okay, the important part is the slope. So we know, what does that slope tell us? That slope tells us that for every extra week of gestation, that infant increases how many ounces in weight? 5 ounces. So that's critically important to the birth weight of the child, the weeks of gestation, because every week means another 5 ounces. So if you have a baby that's very small and tiny, or you have multiple births or something like that, that's why doctors are so anxious to, in case of multiple births, to make sure they get it complete as many weeks of gestation before they wind up with a birth. And additionally, on the other end, right, you don't want babies that are too big. There are issues with babies that are too big also. So this kind of formula, this idea of 5 more ounces every week, that might concern you when a birth is delayed, and that might encourage a doctor at a certain point to induce labor, because he doesn't want that gestation waiting another week because the infant's too large already. Right? So this is important clinical information, right? So in this case, the effect is not only is it statistically significant, I'll roll this back so we can see the circles where they belong. Not only is it statistically significant, but it's really clinically important, right? And you know, so those of you guys that have worked in hospitals or in in births and so on and so forth, you guys know that they're always keeping an eye on how many weeks of gestation or what the progress of the pregnancy is. And weeks of gestation, the number of weeks is critically important as well. It's considered critically important. Okay, so this is the reason why it is. Okay, so that's pretty good, right? 34% of the variability in the birth weight is due to the increase in the number of weeks of gestation. And we had a little bit of an effect also from the age of the mother. I'm going to do some really nuts here. I'm going to go over here and go to Analyze, and I'm going to go to Regression, and I'm going to go to Linear Regression. And you know, look at this box where it says Independence. In that box, I'm going to take the age of the mother. I'm going to move that in there at the same time. So now I have 2 independent variables, completed weeks of gestation and the age of the mother. So I'm going to go ahead and click OK. Now, there's a number of ways that you could do this analysis, but I'm going to click OK. And I am going to go down here and I'm going to take a look at the R value, which is 0.6. That's higher than before for either analysis independently. And I'm going to look at R squared. Now, my R squared is almost 37%. What was it before? It was like 3%, and it was 3% in the case of the age of the mother. It was 33 or 34% in the case of the number of weeks of gestation. But now I've created a new formula here. And in this formula, I have 2 independent variables, x1 and x2, or beta 1 and beta 2, right? And each one of those has its own constant. So if I were to write this formula out, y, or the weight of the child, weight of the child is equal to, let's see, 0.6. Again, I'm rounding. Don't do this. I'm just doing this to make things simpler for myself. 0.6 times the age of the mother, MH, plus 4.8. This is pretty ugly, but you get as long as you can hear me speak, you know what I'm doing here, times the weeks of gestation, weeks, right, minus 85. Now this formula is better at describing the relationship between these independent variables and that dependent variable. In fact, now almost 37% of the variability is explained by including 2 variables instead of just 1 variable. Well, gee, if I can do that, what if I included not just that, But what about if I included things like how much vitamin D that the mother gets, what the level of vitamin D in the mother's bloodstream is during the course of pregnancy, or what her diet's like during the course of, how many calories she eats a week during pregnancy, how many, and half a dozen other numerical variables. Each one of those may have some impact on what determines the birth weight of the infant. So each one of them has the possible advantage of helping me increase my understanding of what causes, what contributes to the birth weight of the baby, but also makes the formula I create more predictive, right? So, gee, I can keep adding these things. Well, what am I doing here? I'm using multiple independent variables to increase my understanding of what affects the dependent variable. I'm doing what's called a multiple regression. Okay. So what do we got to be careful about multiple regression? We got to be careful of including variables that are really the same as other variables you're already using. For instance, let's say that as an independent variable, I would like to use BMI. I'm going to use BMI to predict a person's cholesterol level, right? So I do my analysis and so on and so forth. I said to myself, you know, that's very interesting, but you know, I think that I can make this a better analysis if I add another independent variable. I know what I'll add. I'll add weight. So I'll see if a BMI in a person's weight indicates it's a better indicator of their cholesterol level than just BMI is. There's a problem with that. Can you see what the problem is? Weight is already part of BMI, right? In other words, that it's really you are using really two variables that really are interdependent already. So you want to avoid that. When you do multiple regression, you want to avoid that. Okay, and there's ways for testing for that as well. You know, there's a couple of good links on the internet that go into a bit more advanced version of understanding linear regression, especially multiple linear regression, and especially something I may do an online version next week, which is kind of finals week for us, but we're doing an online project of final. So I may do a short session next week on just introducing, just like a very 30-minute introduction to logistic regression. Okay, what do we mean by logistic regression? Well, logistic regression, what we're looking at is we're looking at a situation where the thing that we want to predict is not a numerical variable, it's a logical outcome. What is a logical outcome? Well, like a yes or no or a true or false. For instance, is a person diabetic or is a person not diabetic? In the case of the data that we have here, is the infant premature or is the infant not premature? Right? So in logistic regression, we want to create a formula or a numerical way of determining the probability that an infant might be premature or that a person is diabetic based on a formula. In other words, what's the probability? This is the probability. So right now, if I were to go in here and I were to look at how many babies were premature out of 800, and it turned out to be 80, the probability in this population that a baby would be premature is 10%. But boy, wouldn't it be great to be able to, in other words, if I was just looking at a random birth, without any other knowledge, I would only be just a name, let's say, or a subject number. I would be able to predict that 10% chance that baby's going to be premature. However, I want to be able to predict a better method of predicting whether a baby is premature or not. So I might want to do a regression that'll tell me if I examine this independent variable, like perhaps something like whether the mother's married or not, how does that affect the probability of the infant being premature. See, there's a very interesting difference there. In one case, with simple linear regression and with the correlation, we're looking at two numerical variables. How does this value affect that value? In logistic regression, we're trying to determine how this value, and it could be a numerical variable, usually a numerical variable, can be categorical variables also. How do these variables, including numerical categorical variables, tell you more about the probability of whether that particular birth is likely to be premature? So now, if you know the mother's unmarried, now maybe the probability goes from 10% to 20%. And if you know that the mother smokes, maybe it goes to 22%. And if you know that the mother drank during pregnancy, maybe it goes to 30%. So now you can use these variables in logistic regression to give you a way to predict the probability of a binary outcome, a probability of going one way or the other. Why logistic regression? Because logistic regression is generally the way you describe a yes, no, or a true, false kind of situation. Premature or not premature, diabetic or not diabetic. So now we set up that formula that way. So I'm gonna ignore that for now, just to give you that kind of little introduction, and we'll do that next week. Next week I'll be online so that if you have questions, I'm going to concentrate next week since it's really finals week. I'm going to concentrate next week on being available online, maybe here, maybe not. We'll see. Maybe I'll send out an email to find out if people are interested in coming here or just being online. So if anybody wants to come in here, I'll try and be here next Monday for just help with projects or question and answer and so on and so forth. And maybe we can do like a half hour as part of that. It's just observing me do a quick logistic regression. Why is all this so important? Why am I emphasizing correlation, linear regression, multiple linear regression, logistic regression? Because so many studies these days, so many things you're going to read in the literature, use those kinds of analyses to enlighten you about the relationship between the various variables. And why do they use that instead of chi-square and this up? Because it's the nature of the data, number one, numerical data, for instance. Some of it might not be applicable to those other types of analysis, but it's also because it gives you a window on what ifs. What if we were able to make this bigger or make this longer, or if we educated, or if we intervened, or if we gave this drug, what would be, or if we made sure that their vitamin D levels were in this range, or what if we did this, how would that affect the outcome? So regression, linear regression, logistic regression, multiple regression are uniquely designed to give you that kind of feedback. That's why it's such a popular analytical tool in statistics. A little bit more complicated. Most people in most introductory statistical courses might get a taste of linear correlation and linear regression, and then go into advanced courses for multiple regression and logistic regression. But it's good to at least know what this stuff is. So let's talk about the projects, right? So on Blackboard. Okay, I'm definitely recording that. Yes. Okay, so on Blackboard, you will notice that there is now a little click here for, where is it? Exam 3 or project option. And if you click on that, where does that take you? Well, that takes us to exam 3 project option. It takes you to a description, exam 3 project. You have the choice of completing a third exam, covering only materials since the second one, which is just correlation or regression. You may also notice that I put a brief assignment on here, correlation and regression. Okay, that brief assignment basically is just what we did in one of these examples, similar to what we just did in one of these examples, right? So that you can get a little bit of practice with it before the exam. Okay, and usual rules. It's technically due December 15th, which is like Sunday night or something like that, and at least the first submission. But you have until the end of the semester to complete it. Just keep in mind, the end of the semester is December 19th is the last day of finals, right? So I need it by then. Technically, I'll probably be doing the work on the 20th, so you guys can stretch it out to the 20th if you need to. But I have to get grades in, so don't stretch it too far. So this first attempt on the homework is December by December 15th. If you submit by December 15th, you can go back in the remaining week. You can go back and do it again, do the assignment again for an increased score. Okay. The assignment, as always, would give you tell you which answers you got wrong, but not give you the right answers. You can go back there and take a look at it. Okay. So the project. So we have a little tab. Okay. So so option A is available now, of course. So option A is that project. So you have a couple of documents there. First document is a description of the project itself. Okay, so what do we want you to do? Okay, so we want you to choose from one of the data set that we've provided here, and I'll go back and show you what those data sets are. And we want you to put together a report. Now keep in mind that if this were brick and mortar, I would be asking you to do a presentation that looks kind of like a poster presentation at a professional organization. For you guys that haven't seen this before, let's see, APHA, American Public Health Association poster session. Let's see if I can get a couple of images here. Okay, so how's this look? Well, yeah, take a look at this. Many people present their research from a podium. They have lecture, like 3 p.m. So Dr. So-and-so or this researcher is presenting in conference room C from 2:30 to 3 o'clock. He's going to present his research on HIV and so on and so forth. Well, obviously, giant conferences like American Public Health Association, tens of thousands of people show up for, they don't have enough conference space for every presenter or every piece of research that might be important for people to see to be able to present it live. So they have large poster sessions. So basically what you see is, this one's a nice one, they got chairs. Usually don't have chairs. That you see is rows, literally rows. You'll see there's other ones that are on the right, rows of these posters. They're professionally printed. We're not going to do that, obviously. They're professionally printed, but if you look at the individual posters, they outline a person's endeavors of research, what he's trying to show, how he's doing it, how he's collecting his data, what his data looks like, descriptive statistics on the populations that he's examining, for instance, his results of his research could include statistical tests, charts, and so on and so forth, and his conclusions and what he wants to do with this in the future, right? So all of that's kind of written very compactly and succinctly on this poster, so that people can walk down this aisle, glance at these posters, and if they see something that, for instance, I'm very much involved in Legionnaire's disease and cooling towers. So if I were walking up and down this aisle, I'd be ignoring the ones on HIV, ignoring the ones on nursing issues and so on and so. But if I saw one on Legionnaire's disease, I'd say, aha, let's see what this guy's working on. I would stop there. And in this case, for instance, you see the actual researchers that are standing by their posters, so someone can actually talk to them about that, ask questions, and so on and so forth. So that's kind of what we want your report to be. Like, what kind of thing would you put on a poster? And if you look, I can show you some examples of posters. You don't be surprised if some of these are students from Hunter, right? Because a lot of them do present here. So you can see that these are rather elaborate, right? But again, remember, this is presenting all their research. Okay, so this one includes a lot of graphics. The graphics are nice. The graphics tell you a lot of information at a glance, rather than have to get up close, and especially for a poster, reading a table. Much harder to read this table than to read this graph, but you get the data presented in both ways. The table is probably more comprehensive, but the graph gives you a quick look at that information. So you might have an introduction into the research. You might have something about what the research question is. You might have the methodology. Here you might have the data, maybe some of these statistical results. Here you might have the results and conclusion, including, the regression analysis, the chi-square value, and so on and so forth. And down here you might have discussion, recommendations and discussions. And down at the bottom here you might have references, articles that are relevant to their research, that their research is based on, and that they use as part of their research, right? So these elements are the kinds of things that we want to see in the report. And you can see, even on this real professional poster, talking about 1, 2, 3, 4, maybe 5 type pages and some charts and tables. Yeah, kind of. Yeah, but you don't have to. When we were doing it brick and mortar, people would go to PowerPoint or something like that and print this out on a piece of paper, and then we would take a poster board and just tack them up. So it was literally would look like this, but kind of like a Frankenstein version of it, taped together and held up with tacks and stuff like that. But that's what we're driving. That's the kind of report that we're interested in. But the actual rubrics of the report, and again, you don't have to get crazy and make it exactly like a poster. Just we want to get that kind of, imagine that this is what you're doing. You're presenting this information to other researchers as they walk by, because you want feedback on this. You're going to continue to do research. You're going to want to go for grants and things like that, or extend your grant and so on and so forth. So you want feedback from other people saying, gee, this is really interesting. Did you consider this? Or this is really interesting. There's a guy over here that's doing this other part of this that you should get together with, right? So you want that kind of feedback. So what should the report contain? It should contain an introduction, probably like that was there. You should probably include some descriptive statistics. In other words, if you were using the data set that we were just working with today, that North Carolina birth, the descriptive statistics might be the distribution of the age of the mothers. It might be a histogram showing the birth weights of the infants. It might be a bar chart showing how many mothers smoked or didn't smoke, how many mothers drank, didn't. So you might have you might have some statistics there to show us, give us a picture of what the population looks like, some descriptive statistics, right? And including the variables, especially the variables you're looking at. You don't have to get crazy about that, just something very simple, right? And you could do that in Excel, you could do that in SPSS, right? A lot of ways you could do that. Section number three is the methods. Okay, how was the data collected? What are the variables? What are the units of the variables? And how did you analyze the data? What statistical tests you used to analyze the data? Section 4 is the results. Show us the tables that you got, your chi-square table, the scatter plot for your correlation or regression, and so on and so forth, if you wind up doing something like that. The results of your t-test, your analysis of variance, your post hoc tests, and so on and so forth. And then finally, the discussions and conclusions. Now, you should also include, at least I think it's up here, you should also include, I want to make sure it's on here somewhere. Okay, other variables. Should also include, I'm going to add it. I'm going to add it there, but you should also include at least 1 or 2 references that are relevant to the variables that you choose, the data set and the variable that you choose to work with. So, for instance, if you decided that you're going to work with, you have your own data set that involves the diabetes and the amount of exercise a person gets. You might want to give us an article that you found on PubMed. We have access to, hopefully the library, you guys are trained to use the library and stuff like that, and go on PubMed or one of the other databases that we have and see if you can't find an article that relates to what you're doing in your analysis, right? And include at least 1 or 2 relevant articles at the end of your poster. I'll add it on as 6, 1 or 2 relevant articles, and so on. So what are your options? Well, one option is that you do an analysis based on flu shot utilization in New York City. If people that are more insured, more likely to get flu shots are people that are native born to the United States, or different boroughs have different rates, so on and so forth. But how are we going to do that? Well, we've given you data here from the New York City Community Health Survey. We discussed that last week. And this data, we gave you several different versions of it. One of them is the full data set for 2013 with all of the 200 questions that they asked in this survey and so on and so forth, and the code book that has all of that data. Well, what we did then is we took a subset of that data that was relevant to influenza. Okay, so, and you have three versions of this, and one of them is the actuals as a subset of the data from that year, from that survey for that year, that has, I think it's 8 or 9 variables, and it's already coded. Now, you don't have to use this data set. I'm going to put it on my desktop. You don't have to use this data set, right? But you're welcome to it. Let me just open this again. I think in here I have, do I have it? There you go. These are the variables in that data set: flu shot, health insurance, race and ethnicity, borough, neighborhood, the rate of poverty in the neighborhood where they're located, their gender, their age, whether or not their nativity, whether or not U.S. born or not, and if they have any, if they're children in the household, and so on and so forth. And you can look at this and see which of these it doesn't have to be all these variables. It could be only a couple of them. You might want to look at the impact of health insurance on someone getting a flu shot and what borough they live in, or health insurance and the rate of poverty in the neighborhood they live in. Or you might want to look at the likelihood of getting a flu shot and what person's age is, and so on. So you can combine a couple of these. You could do a couple of analyses. You could do just one analysis. It's up to you. And this data set has already been prepared for you, coded and everything. I'm about to open it up now so you can see it. Okay, so now you know what happens. The Olympics are in Tokyo next year. And I read an interesting article today because the World Sports Organization, whichever one that generally sanctions all of these different countries' sports groups, is it possibly going to rule to forbid Russian athletes from competing in any international events for the next 4 years, which would mean that they would miss the Olympics in Tokyo, and that's because that they've been quite repeatedly cheating on drug testing, on doping and drug testing, and not individual athletes, as an organized cheating on those tests, and so they're kind of in big trouble. But the reason why I brought up the Olympics is because the Olympics, when you are a diver, right, Summer Olympics, when you're a diver or you're doing one of these other sports that are judged sports, right? Well, you got two elements there. You have how well you perform, and you have the difficulty of your program, right? So if you are going to use my coded data set that I've done all that work for you, and it's all like laid out for you, that's great, right? But you'll be judged a little bit more harshly than if you decided to go into the code book and go into that full data set and find a couple of your own variables. You get a little bit more creative. Then I'm not saying that I'll grade you. I'm not saying that you're going to be penalized for using the data set that I prepared for you. But I am saying, what I'm saying is more likely that if you make a mistake on a data set that you put together yourself and you coded and so on and so forth, I can give you a lot more latitude on that, because you kind of went out of your way to like really stretch yourself and learn a bit more about how to do this stuff. Okay, so it's not so much I'm going to grade it more harshly. It's that I'm going to grade the other one more with a little bit more understanding if you do something that requires you to go a little bit out of your way and do something a little bit more adventurous. Okay, so so that's the particular data set. So now also, let me just open this other data set. Okay, open data, navigate to where it is. Here's our simplified flu data set. And the variables I just mentioned here were in the data view. Here's the variables. Demog1 happens to be age, the age of the person. I don't know why they gave it that variable name, but again, you can see why we like using those labels, right? So what is that Demog1? It's the subject's age. Borough is borough residence, a little bit easier to understand. And you'll notice I also coded in the values for you. Like for the borough, I've coded in what those values mean. So this really is prepared for you to go ahead and work with this and decide, well, I want to work with the borough and whether or not, I want to work with the borough and whether or not they got a flu shot in the past 12 months, right? Maybe I have a feeling that people in Manhattan may be more likely, more affluent, may likely to get flu shots or less likely to get flu shots. Busy or less likely to get flu shots. You might examine that relationship, right? In other words, there's two nominal variables. Each of them are categorical, right? And you have 5 categories for the borough, and you have 2 categories for whether or not a person got 2 values for a person got a flu shot or not, right? So what is that? That's 5 by 2. That's chi-square, right? You're gonna have a contingency table. Boroughs, 5 rows, boroughs, and 2 rows got a flu shot, didn't get a flu shot, so you can do a chi-square analysis to see if there's a relationship between, if there's a significant difference between which boroughs you live in and whether or not you get a flu shot. You can also, perhaps, if you get a little creative, you can maybe create or transform or create a new variable. Maybe I'll do that on Monday, show you. We did it last week. Maybe I'll redo that on Monday, show you how to transform a variable or compute a new variable, create a new variable. Maybe you can create a new variable where you can compare, where you can accumulate all of the boroughs together. And so that you can individually look at the rate that people in Brooklyn get a flu shot versus the rate that people in the entire city get a flu shot. So it would be a 2 by 2 table, borough, Brooklyn, and the entire city. So that 2 by 2 table, you could do an odds ratio for. And then you could repeat it for Bronx versus the entire city and Queens versus the entire city. So you can get an idea of which of those have a higher rate or have higher odds of getting a flu shot if they're in that particular borough versus the rest of the city. Okay, so I can show you how to lay that out. Okay, so we'll talk about that possibly on Monday, but you already have a lot of variables you can work with already. So now let's say you want to get a little bit more adventurous. Want to get a little bit more adventurous, we have, let me go to Blackboard again. We have also other data sets here. We have data from the Framingham study that involved doctors, and it was an extended study, a prospective study where they followed tens of thousands or thousands at least of doctors to determine which ones would eventually develop heart disease and so on, cardiovascular disease and so on over a period of time, which of them smoked and so on and so forth. So you have data from that study here. You have a study on digitalis. You have a study on physical activity and the transit system. You have several other data sets that you might want to look at. This one involves youth, New York City youths, and types of risky behavior that they might be involved in. Okay, and but you might want to consider taking a look at some of that data, and you can also use some of your own data. If you're working in another course and you have a project you're working on, I have no problem with you taking the data that you're using in that other course and using it for this project. Doing an analysis using SPSS, using one of the techniques that we've learned, and submitting a project based on that. Okay, so let me just show you the entire data set as an SAV file, save as. Okay, and I go here, say file, open data. Oops. Simplified. Here's the full data set. Okay, and here's a whole bunch of numbers up there, right? So for instance, mood 1, a whole bunch of numbers in there. Well, obviously you don't know what mood 1 is. All you can see are those numbers. So we go into the variable view, see mood 1 here. We can see a label that has carried over. And that label, oops, let me undo that. That label tells us that that question was, during the past 30 days, how often did you feel nervous? Right, mood 2 is that particular variable. What is your age? Demog 1 is what is your age, and so on. Okay, so that's very nice for what is your age, because that's a numerical variable, right? But for instance, if we go here to borough, for instance, which is already in the other database, borough of residence, right? Okay, so that makes sense. That's a borough is borough of residence. But if we go over to values, we go over to values, it's not coded. It doesn't say what each of those numbers, what 1 represents, 2 represents, what boroughs they are. So where are you going to find that information so you can add it to these values? Well, I've also given you a code book. And in the code book, if you open the code book, you can look up what the variable borough, what the values are for the variable borough, if I spell it right. Okay, here's boroughs. Let's see if I can find the variable. There it is, variable borough. And in that variable, 1 represents the Bronx, 2 represents Brooklyn, 3 represents Manhattan, 4 represents Queens. So we can go back to that variable and we can code that information into that variable. Okay, as you've seen us do before. In other words, go in here to our variable view and tell it that for borough, what did I say, borough here? See if I can't find it again. For borough, if I go into values, now I can tell it that 1 represents the Bronx. I covered it now, so I'm not sure what it is, and 2 represents Queens or whatever. Right? I don't know that that's exactly right because I covered it up. Maybe I can get it to scroll down. Up 1 is Bronx and 2 is Brooklyn, and so on. And you can code all these things. And they have information, they have variables in here when where they ask people about their consumption of fruit, about whether or not they've had an asthma attack, whether they've been told that they have diabetes during the past 12 months, type of health insurance that they have, so on and so forth. So you can see there's a lot of different elements to this particular survey. And you can just pick out a couple of these variables and say, gee, I'm really interested in smoking status more than anything else and how it affects a person's health. So maybe, or maybe how it's distributed in the population. Are younger people smoking more than older people are, for instance? So you can develop your own study, your own poster project, and put it together and submit it as a project. Okay, and that's for you guys that are adventurous, don't mind taking a little bit of a chance, that want to be judged a little less rigorously, right? But you guys, if you're nervous about that, you don't feel comfortable with that, you can use the prepared data set that I gave you. And all these reports are your own work, so there's no right or wrong answer here. It's basically take the tools that we've given you and take the data that sounds most interesting to you and do something interesting with it, do something creative with it. Okay. Okay. So let's stop there. And on Monday, this coming Monday, the exam and the exam will be available. As of right now, you have the information you need available for you to work on your project. The exam will be available by Monday. I'll probably get it up a day or two before. So if you check Blackboard over the weekend, I'll probably make it available a little sooner. Both of them are due by December 19th. If you're really stuck, I can stretch a day, but I need to get all the grades in so I can work on them over the weekend and get them inputted.